Hello students, welcome back. Well, in the last class, we did work done. That is work done in a reversible and isothermal system and a simple work done. So work done in an isothermal and reversible system, as you can see here, is also known as the maximum work done. Because the work done under reversible condition is always maximum. Now since we are heading towards first law of thermodynamics, before moving into the first law of thermodynamics, we'll be doing some thermodynamic properties which are used there, thermodynamic quantities in fact. So we'll talk about thermodynamic quantity. We call it internal energy. Internal energy is many a time denoted by either capital E or capital U. Well, what is internal energy? Listen to the definition carefully. Internal energy is the part of energy stored within a substance, or we can say it is the total energy stored within a substance. So internal energy is the energy stored within a substance. It is a sum of different type of energies. Every substance has got electrons, protons, neutrons. So it has got electrical energy, magnetic energy. These fundamental particles, atoms, molecules, or we talk about electron, they keep on rotating on their mean positions. That way they generate momentum also, the angular momentum. So internal energy is a sum of electrical energy, magnetic energy, vibratory, oscillatory, rotatory, a lot of energies they are there in a substance. The sum of all these energies is known as internal energy. So every substance has got some energy stored within it. For example, if I talk about water, it has got a lesser energy as compared to if I talk about say gasoline, it has got a higher energy. If I burn gasoline, I get lot of energy in the form of heat. Now, where from this energy is coming? Because we know that law of conservation of energy states that energy can neither be created nor can be destroyed. So if combustion of gasoline is giving us large amount of energy, that means that energy was stored somewhere in the gasoline. That is the internal energy of gasoline. On the other end, if you try to burn water, you will hardly get any energy. Because it does not have energy, it has got a very less amount of internal energy. So internal energy is the sum of different types of energies, and it is the energy stored within a substance. We cannot measure internal energy of a substance because it is very difficult. It is very difficult to measure the electrical energy on such a smaller extent or such a smaller value. Such small electrical energy, magnetic energy, vibratory, oscillatory, angular momentum, such small values we cannot measure. We don't have those apparatus. That's why it is difficult to measure internal energy of a substance. But we can easily measure the change in internal energy. I'll tell you how we can measure the change in internal energy. That also I'm going to teach you. So if we talk about internal energy, I can say that it is the sum of different types of energies stored within a substance. Now change in internal energy, it is represented by delta E or delta U. That is always internal energy of product minus internal energy of reactant. So suppose I got a reactant that is getting converted to product. The internal energy of reactant is say 8 kilojoule and that of product is say 10 kilojoule. Product is at higher energy. So the difference of energy is of 2 kilojoule. That means, if here in this case, that means since the positive sign we have got, that means the energy is absorbed by the system. So this is, here we can see absorption of internal energy. So here in this case, the change in internal energy is 10 minus 8, that is 2. The positive value indicates that the energy is absorbed during the reaction. Because you can see that the reactant is at lower energy, whereas the product is at higher energy. That means the reactant is absorbing 2 kilojoule of energy. That's why it is getting converted to 10 kilojoule. So this is internal energy change. Now the question which comes to our mind, how we can calculate the change in internal energy? See here I have given you that example. Suppose I've got a piece of coal and I'm burning that coal. I don't know what the energy of that coal is. After combustion, that coal is getting converted to ashes. I don't know what the energy of those ashes are. But I know one thing, I can calculate the difference of energy. If I'm burning coal, the energy is coming out in the form of heat. That heat I can easily measure by calorimeter. Suppose I have got 10 grams of water and I am burning that coal by absorbing the heat which is given out by the coal. The temperature of water is increasing, and suppose it has increased by 10 degrees Celsius. That means 100 joules of energy is given out. 100 calorie of energy is given out, because we know 1 calorie is the amount of energy that is required to raise the temperature of 1 gram of water by 1 degree Celsius. So if I've got 10 gram of water and on burning coal, the heat which is given out is raising the temperature of 10 gram of water to say 10 degrees Celsius, that means 100 calorie of energy is given out. Law of conservation of energy states that if coal is losing 100 joule of energy, the energy of ashes is lesser by 100 calories. Whatever will be the energy of coal, I don't know. Whatever the energy of ashes, I know one thing for that the energy of ashes is 100 calorie lesser than the energy of coal. So this is how we can calculate the change in internal energy, although we don't know the internal energy of the reactant and the product, but we can easily calculate the change in internal energy. The next thermodynamic property about which we'll talk here, and this is perhaps very widely used in your standard, we call it enthalpy. Enthalpy. Well, enthalpy is represented by capital H, and the change in enthalpy is represented by delta H. So delta H is what? It is enthalpy of product minus enthalpy of reactant. Enthalpy, this term you might have used in your lower standards also. Enthalpy change. Enthalpy is what? Enthalpy is the part of internal energy that can be converted to heat or vice versa. Only that part of internal energy which can be converted to heat will be stated as enthalpy. I give you one example for that. Suppose I got a cracker or a bomb. If I'm exploding that bomb, the chemical energy is getting converted to heat energy, light energy, and sound energy. Only that part of chemical energy which is getting converted to heat will be called enthalpy. So enthalpy is what? It is the part of internal energy that can be converted to heat or vice versa. The part of heat which can be converted to internal energy. My dear students, since we are studying thermodynamics, that simply means that this term is very important, because here we are dealing with energy in the form of heat. You might have done one thing in the structure of atom, ionization energy. What is ionization energy? Ionization energy is the minimum amount of energy that is required to remove the most loosely held electron, that is the valence electron, from an isolated gaseous atom. So ionization energy is the minimum amount of energy that is required to remove the most loosely held electron from an isolated gaseous atom. But if this energy is in the form of heat, we call it ionization enthalpy. So ionization enthalpy is the minimum amount of heat energy that is required to remove the most loosely held electron from an isolated gaseous atom. So whenever the energy is in the form of heat, we call it enthalpy. I give you one example for this. Suppose reactants, as in this case, reactants have got 8 kilojoules of energy, and product they have got 10 kilojoule of energy. Then in that case, enthalpy change is equal to 10 minus 8, that comes out to be plus 2. Positive sign in this case indicates it is endothermic. So whenever a reaction is endothermic, the sign of delta H is always positive. Now I give you a reverse reaction. Suppose I got a reactant that is getting converted to product. The energy of the reactant is 10 kilojoule. When it is getting converted to product, the energy is 8 kilojoule. You know energy can neither be created nor can be destroyed. So when it is getting converted from 10 to 8 kilojoule, that means it is losing 2 kilojoules of energy. So here I will write plus 2 kilojoule of energy. That means this is exothermic. Now we'll use the same formula, that is delta H is equal to 8 minus 10. The answer comes out to be minus 2. Minus sign in this case indicates that it is exothermic. So whenever a reaction is endothermic, its sign is positive, and whenever a reaction is exothermic, its sign is negative. So negative sign indicates that it is exothermic reaction. Well, here I'll give you a general expression. You have to remember it as such. That is delta H is equal to delta E plus P delta V. That is, if a small amount of heat energy is given to a system, some part of that heat energy will be used to increase the internal energy, whereas with rest of the part, the system is going to do the work. We know P delta V is the work done by the system. So delta H is equal to delta E plus P delta V. My dear student, now I'm going to tell you different type of enthalpies. I'm just going to dictate their definition and you have to write it down. I'm not going to write it here. I'm just going to explain you. And many a time in your exams it is asked like what do you understand by enthalpy of formation? What do you understand by enthalpy of combustion? Enthalpy of neutralization? Such a things. So here we'll see. First I'm telling you enthalpy of formation. As you know that enthalpy is what? It is energy. And energy has got a dimension, that is joule, kilojoule, calorie, kilocalorie, something like that. So its dimension which I'll use and which is commonly used is kilojoule per mole. So my definition will be in accordance to these dimensions. Suppose carbon is reacting with hydrogen. This is in the solid state, this is in the gaseous state, and that is giving me CH4. That again is in the gaseous state. And the heat energy which is given out is X kilojoule per mole. So this X kilojoule per mole is the enthalpy of formation of methane. It is the amount of heat energy. Remember this thing, what is enthalpy of formation? It is the amount of heat energy or enthalpy change accompanying the formation of 1 mole of a substance. So enthalpy of formation is the enthalpy change accompanying the process of formation of 1 mole of a substance. This is enthalpy of formation. Second, we have enthalpy of combustion. Now carbon in the solid state plus O2 will give me CO2. And suppose in this process the energy is given out, say X kilojoule per mole. So X kilojoule per mole is what? It is the enthalpy of combustion of carbon. So what is enthalpy of combustion of carbon? Again, the statement, please listen to this carefully, and if you want you can write it down. It is the enthalpy change accompanying the process of combustion of 1 mole of a substance. Now one question will come to your mind, that X is the enthalpy of combustion of carbon. But can it be the enthalpy of formation of CO2? Yes, it can be. And generally its value is minus 393.5 kilojoule per mole. So minus 393.5 kilojoule per mole is the enthalpy of combustion of carbon, and it is also the enthalpy of formation of CO2. So this is what enthalpy of combustion is. Enthalpy, again, I'll repeat it. Enthalpy of combustion is the enthalpy change accompanying the process of combustion of 1 mole of a substance. Then comes enthalpy of neutralization. Enthalpy of neutralization. We know this very well. What is neutralization? An acid is neutralized by a base and vice versa. So suppose you have got 1 mole of HCl that is neutralized by 1 mole of a base. Likewise, if I have say H2SO4, 1 mole of H2SO4 is neutralized by 2 moles of NaOH. Likewise, if I have H3PO4 that is neutralized by 3 moles of NaOH. By writing these reactions, I just want to make one thing clear, that it is not always that 1 mole of an acid is neutralized by 1 mole of a base. It is not always like that. So we cannot say that it is the enthalpy change accompanying the process of neutralization of 1 mole of an acid by 1 mole of a base or vice versa. But one thing is for sure, you can see that 1 mole of an acid is not neutralized by 1 mole of a base, but 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base. 1 gram equivalent of HCl is what? Its equivalent mass, that is 36.5. That is neutralized by equivalent mass of NaOH, that is 40. Likewise, in case of H2SO4, you can see that 98 grams of H2SO4 is neutralized by 80 grams of NaOH. Then the equivalent mass of H2SO4 we know is 49. So 49 grams of H2SO4 will be neutralized by how many grams of NaOH? That comes out to be 40. So 49 grams, that is the equivalent mass of H2SO4. See, again I am repeating it. 98 grams of H2SO4 is neutralized by 80 grams of NaOH. So 49 grams, which is the equivalent mass of H2SO4. The equivalent mass of H2SO4 is 49. So 49 grams of H2SO4 is neutralized by 40 grams of NaOH. So this is for sure that equivalent mass of an acid is neutralized by equivalent mass of a base. So in its definition, we do not use moles. We use number of gram equivalent or equivalent mass. So what is enthalpy of neutralization? It is the enthalpy change accompanying the process of neutralization of 1 gram equivalent of an acid by a base or 1 gram equivalent of a base by an acid. Do remember this definition because these definitions, they are really important. Many times they are asked in the exam. So enthalpy of neutralization is the enthalpy change accompanying the process of neutralization of 1 gram equivalent of an acid by a base or 1 gram equivalent of a base by an acid. Likewise, we have ionization enthalpy. Ionization enthalpy. This I have already taught you that it is the enthalpy change accompanying the process of removal of most loosely held electron from an isolated gaseous atom. So most loosely held electron that belongs to the valence shell. After that we have electron gain enthalpy. Electron gain enthalpy. Now suppose I have got an element like fluorine. If I add an electron to fluorine, it will get converted to fluoride. It will become stable because its electronic configuration initially was 2,7. Now it has become 2,8. It has acquired a stable configuration of noble gas configuration. Stability means lowering of energy. That means the energy of fluorine was higher and the energy of fluoride is lesser. So according to law of conservation of energy, when it is changing from high energy to low, it will lose energy. So in this case, we'll get some energy. This is the amount of energy which is given out. This heat energy is known as electron gain enthalpy. So what is electron gain enthalpy? The electron gain enthalpy is the enthalpy change accompanying the process of addition of an electron to an isolated gaseous atom. My dear student, here in this case, it is exothermic, whereas it is not mandatory that it is always exothermic. It can be endothermic. For example, if I talk about nitrogen, the configuration is 2,5. And if I further break down 5, it becomes 2s2, 2p3. That means a stable electronic configuration. So it does not have a tendency of gaining an electron, but I am adding an electron to this. If I have to add an electron to this, I will use some energy also, because it does not have a tendency of gaining an electron. So in this case, if it becomes N negative, or on further adding it becomes N2 negative, or it becomes N3 negative, in this case we are using energy, we are applying energy. That means it is endothermic. So addition of an electron to an isolated gaseous atom can be exothermic or endothermic. So it is the enthalpy change accompanying the process of addition of an electron to an isolated gaseous atom. Likewise, the last one is the lattice enthalpy. Lattice I'll correct it. Lattice enthalpy. We'll see what lattice enthalpy means. In a crystalline solid, A definite number of cations combines with a definite number of anions to form a crystalline solid. For example, 1 mole of Na positive combines with 1 mole of Cl negative to give you 1 mole of NaCl. Likewise, 1 mole of Ca2 positive combines with 2 moles of Cl negative to give you 1 mole of CaCl2. Likewise, 1 mole of Al3 positive plus 3 moles of Cl negative gives you 1 mole of AlCl3. So you can see that it is not always necessary that 1 mole of cation will combine with 1 mole of anion. It is not always like that. But whenever a cation combines with an anion, there is always a prominent attraction. Wherever there is a prominent attraction, large amount of energy is given out. So this process is exothermic. So what is lattice enthalpy? Lattice enthalpy is the enthalpy change when a definite number of cations combines with a definite number of anions to form 1 mole of crystalline solid. So it can be 1 mole of NaCl, 1 mole of CaCl2 or 1 mole of AlCl3. 1 mole of NaCl is formed by 1 mole of Na positive and 1 mole of Cl negative. 1 mole of CaCl2 is formed by 1 mole of Ca2 positive and 2 moles of Cl negative. Likewise, 1 mole of AlCl3 is formed by 1 mole of Al3 positive and 3 moles of Cl negative. So the number of cation and anion is not fixed. It can be anything. But the crystalline solid which is formed is always fixed. That always has to be 1 mole. So it is the enthalpy change accompanying the process of formation of 1 mole of a crystalline solid when a definite number of cation and anion combine together. We can also put it in a reverse way also. Law of conservation of energy is applicable there. I can say it is the enthalpy change applicable to break 1 mole of crystalline solid into its respective cations and anions. So that again is lattice enthalpy. So this is what a lattice enthalpy is. Now we'll see the enthalpy change in the formation of a ionic solid. Whenever an ionic solid is formed, what enthalpy change occurs there? Here I'll give you an example of formation of sodium chloride. For that, suppose sodium in the solid state combines with Cl2 in the gaseous state and it gives me NaCl in the solid state. Now what happens here, you will have some enthalpy change. I'll call it enthalpy of reaction. We'll take it in a generalized way. Sodium, I am replacing it by metal in the solid state plus non-metal in the gaseous state will give me salt in the solid state. And the enthalpy change is enthalpy of reaction. This whole process comprises of some steps. We'll see that. Initially, out of large number of metal atoms, one metal atom will come out. That is in the gaseous state. In a metal, large number of atoms, they are joined together. They have some attraction. Now what we are doing? We are taking out one atom so that it can react with a non-metal. Out of large number of atoms, we are taking out one atom. We are overcoming that force of attraction which was there between them. That means we are using some energy. The energy which we use is known as enthalpy of atomization. So since we are using energy, it is endothermic and the sign is positive. What is enthalpy of atomization? It is the minimum amount of heat energy that is required to remove a single atom from a group of atoms. So single atom of any substance, it is always in the gaseous state. Now the question comes, why I am removing one atom? Because I have to ionize it. And you know that ionization energy is the minimum amount of energy that is required to remove the most closely held electron from an isolated gaseous atom, single atom. Second, what I have to do, I have to break the bond between two halogens so that I can get two non-metal, so that I can get 2x. You have X single bond X. It is X2 and X2 is not going to react until you break this bond. If you break this bond, it will get converted to 2x. So here in this case, I can have 2Cl2, I can have 2Cl from Cl2 or 2F from F2. After that, metal is going to lose electron. This metal will lose electron. It will become M positive in the gaseous state. The amount of energy which we are using here is ionization enthalpy. This we have already done, and since we are using energy, the sign is positive. The electron lost by metal is gained by the non-metal, and it will become X negative in the gaseous state. Since it is gaining electron and becoming stable, it will lose energy, and that heat energy is electron gain enthalpy, and its sign is negative because it is exothermic. Now we have got a metal cation in the gaseous state and a non-metal anion in the gaseous state. They are experiencing attraction, so they are coming closer to each other. Due to prominent attraction, they are coming closer, they are losing large amount of energy. The energy which they are losing in this case is known as lattice enthalpy, and its sign is negative. This whole cycle is known as Born-Haber cycle. And according to this, the enthalpy change of a reaction is equal to enthalpy of atomization plus enthalpy of ionization plus enthalpy of dissociation, which you can see here. I'll show you. Here we have used some energy, that is enthalpy of dissociation, and its sign is also positive. As I have told you that X2 is not going to react, you have to break it, you have to apply some energy, that is known as enthalpy of dissociation. Minus now the exothermic steps, that is electron gain enthalpy plus lattice enthalpy. So here you can see these are endothermic steps and these are exothermic steps. If the energy given out in exothermic steps is more, if the energy given out in these steps is more, the overall delta H will become negative, the process will become exothermic, and the reaction will occur. This will be a spontaneous process. So this is something about enthalpy and Born-Haber cycle. Here you can see Born-Haber cycle. Delta H of reaction can be calculated like this. Now we'll move on to first law of thermodynamics. First law of thermodynamics. Well, first law of thermodynamics is simply the law of conservation of energy. And it states that energy can neither be created nor can be destroyed. It can only be changed from one form to another. So this law is very much applicable in thermodynamics, this law of conservation of energy. I give you one example for that. Suppose here I have got a cylinder. This cylinder is fitted with a piston, airtight piston, as we have done in the last class also. And a gas is filled inside it. I have supplied it some heat energy. The external pressure or the atmospheric pressure is constant. So the heat which I am supplying is against constant pressure, that is del QP. Suppose this energy which I have supplied is say 10 kilojoule. By that energy it will do some work. So the heat energy which I am supplying is at constant pressure. Now suppose the heat energy which I have given here is 10 kilojoule. The gas will expand, the piston will move upward. That means the gas is doing some work. It is pushing the piston upward. It is doing some work. If I measure this work, this work which is done by the gas will always be lesser than 10 kilojoule. It will never be equal to 10 kilojoule. I have supplied a heat energy of 10 kilojoule, but the work done is not equal to 10 kilojoule. Say it is 6 kilojoule. Now the question comes to my mind, where 4 kilojoule of energy has gone? I have supplied 10 kilojoule. The work done is of 6 kilojoule. Where the 4 kilojoule of energy is going? Well, law of conservation of energy has got an answer for that, and that is applicable over here. According to law of conservation of energy, that 4 kilojoule is used to increase the internal energy of the gas. The gas molecules, they've got some internal energy, some kinetic energy, which they are moving in the cylinder. Now suppose if they are to push the piston upward, their kinetic energy has to be say 10 kilojoule. And their kinetic energy right now is say 6 kilojoule. So when I'm supplying energy from 10 kilojoule, they will absorb energy. They will increase their kinetic energy from 6 to 10. That means they will absorb 4 kilojoule energy. They will absorb that 4 kilojoule energy. After that, they will do the work of 6 kilojoule. So when I have supplied 10 kilojoule of energy, the work done is say 6 kilojoule. The 4 kilojoule energy is used to increase their internal energy. So whenever I am supplying energy to a system, the work done is never equal to the energy which is supplied to the system. It is always lesser because some amount of that energy is used to increase the internal energy. That's why here in this case, we can say that if del QP is the amount of energy supplied to the system, then some part of it is used to increase the internal energy and rest part is used to do work. This is the expression I have got. And the work in this case can be of expansion as we are studying here. This first law of thermodynamics, this is the mathematical expression of first law of thermodynamics and it is applicable everywhere. If I am talking about work of expansion, this equation becomes del QP is equal to delta E plus P delta V. In this expression, you will see that only pressure is constant. So if small amount of energy is given to a system, the part of that energy is used to increase the internal energy. Rest part is used to do the work of expansion. My dear student, we have already done. If you can see in case of enthalpy, what we have done, what I have told you about enthalpy, enthalpy is delta E plus P delta V. So both the formula they are same. That means the amount of energy supplied to a system at constant pressure, the amount of heat energy supplied to a system at constant pressure always results in increase in enthalpy. That is del QP is always equal to delta H. This is the expression we have got from here. Another example I'll give you. Suppose I am welding this piston over here. I am not allowing this piston to move. It cannot move. If piston cannot move, then change in volume is 0. If change in volume is 0, that means P delta V is 0. In that case, we can say del QV is equal to delta E. So heat supplied to a system at constant pressure will result in increase in enthalpy, and heat supplied to a system at constant volume will result in increase in internal energy. This is what the first law of thermodynamics is. And that's all for today's class, because in the next class, I'll be telling you something about applications of first law of thermodynamics. And when we say application of first law of thermodynamics, that basically means bomb calorimeter, then relation between heat capacity at constant pressure and constant volume, and Hess's law. So this is what we are going to do, and Hess's law is very important for you. So don't miss the next class. Do watch that video also, and please do subscribe my channel so as to get all the notifications at time. Thanks for joining. Thank you very much.